Good evening. This is the power of negative reasoning. And this is a joint work with Susanna Derzende, Jakob Nordstrom, and Dimitri Sokolov. In this paper, in this work, we discuss issues about refuting propositional formulas using algebraic methods. Proof systems like Untitled, polynomial calculus, Sherali-Adams, and sum of squares. For the sake of this talk, we will only focus on polynomial calculus, but most of the ideas that we discussed in this talk will transfer with very little effort to the other proof systems. So to make a long story short, if we consider like a clause, which is the basic item of discussion when dealing with propositional formulas, if we want to encode it as an algebraic representation like a polynomial equation, we can decide to use or not to use dedicated variables to represent negative literals. If we don't use these dedicated variables, then, for example, this clause requires a polynomial with 4 monomials, while if we use this if we use this variable for negative literals, this clause can be encoded as a single monomial. And it turns out that for all those 4 algebraic proof systems, this idea of using dedicated variable for negative literals is very convenient. Indeed, there is an exponential separation between the same proof systems with and without the variable for negative literals. So there is an exponential advantage of using these additional variables. Okay, let's be more precise. What do I mean when I say refute a CNF formula? Well, we have a bunch of clauses, and the refutation of a CNF formula is essentially a proof that the formula is unsatisfiable. The most common way to refute a CNF is to use a resolution proof system. Concretely, the clauses of the formula are used as initial assumption, and from those initial assumptions we can derive new and new clauses until, if it is the case that from those clauses we using this derivation we can derive the empty clause, well, the empty clause is unsatisfiable, is false. Therefore, it means that one of the initial clause must be false, whichever is the assignment that we give to the variables, because because as we showed, the empty clause is derivable from those initial clauses. So this is a refutation of the CNF. This is the actual rule used to do inference in resolution. You see that xi cannot be simultaneously true and false. Therefore, either from those two clauses, either A or B must be true. The size of a refutation in resolution is the number of clauses in the refutation, and the width of a resolution refutation is the size of the largest clause contained in the refutation itself. Now, let's move beyond resolution, because unfortunately resolution has serious issues. It cannot count, and there are several formulas which are connected with counting principles that are very hard to refute for resolution. They require exponential size refutation sometimes. Therefore, it's natural to focus the attention on proof systems that are able to use this counting reasoning. In particular, there are several proof systems, and polynomial calculus is one of them, which deal with algebraic reasoning. Let's see what I mean. Consider this CNF formula. We can encode each clause as a polynomial equation. For example, this clause is true whether one of the two variables is equal to false. And this is exactly what happens here oh, there is a typo. This should be x3, like it is here. So once we have these algebraic, polynomial equations, we can use algebraic reasoning to deduce new polynomial equation. Here I'm not, as you see, I'm not writing this equal to 0, but all these polynomials are actually implicitly polynomial equations, and the equal to 0 is implicit. Now, at some point, we derive the equation 1 equals 0. But 1 equals 0 is unsatisfiable. This means that one of the initial equation must be, it's always falsified, whichever is the assignment that we assign to the variable. Therefore, the set of initial polynomial equation is unsatisfiable. Let's go on and let's specify more precisely what I mean by algebraic reasoning. For example, here we have the formal definition of polynomial calculus. Polynomial calculus is a proof system defined on a specific field. Given the initial CNF, all the clauses are encoded as polynomial equations, and a line in polynomial calculus is either one of the initial equation or is a Boolean axiom, an axiom that says that the variable can only be 0 and 1 valued. Or if we have a polynomial equation, we can multiply it by a variable. If we have two polynomial equations, we can take any linear combination of it, and this is still a valid polynomial equation. In this system, a refutation is the deduction of the polynomial 1. The size of a refutation is the number of monomials in the refutation, the cumulative number of monomials, because counting the polynomial is not enough, because polynomials can be very, very large in terms of number of monomials. The degree of a proof is the maximum degree among all the polynomials occurring in the proof. So there is an issue with why encoding clauses as polynomials or polynomials equation. In particular, see this example. If you have like the disjunction of a lot of positive literals, the polynomial equation that corresponds to this clause has an exponential number of monomials. So this issue makes the direct encoding not very efficient, not very convenient to use. So one way, so is it possible to avoid this explosion in the number of monomials? But one way was proposed in this paper, Aleknovich and others. And the proposal was to add new variables. For each variable xi, to add a variable xi prime that represent the negative literal not xi, and few axioms that says that basically xi and xi prime are of opposite values. Well, this surely fixes the problem with the explosion of encoding the clauses, because see, those clauses can be both encoded as as polynomial equations with a single monomial each. And it turns out that using this new encoding, it is possible, for example, to express in polynomial calculus all the refutations in resolution. Anything that can be done in resolution within a certain size and width can be done in polynomial calculus using these variables for negative literals more or less in the same size and degree. So we did this. Did we solve the issue then? But well, there are several issues with this. There are several problems with this idea. First, we are doubling the number of variables, which in practice is very bad. I mean, the problem becomes much more difficult to handle if we just double the variables. Also, several solving methods, for example, based on Gerbner basis computation and so on, would substitute will eliminate, like for example, the prime variable and substitute it with the binomial, basically making this prime variable useless and going back to the original encoding, which is inefficient. So maybe it's not worth to double the variable. Maybe it's not an issue at all. After all, it's true that we cannot express resolution easily without this negative, without the variable for negative literals. But the polynomial calculus proof do not necessarily need to mimic the resolution proof. So maybe there are other proofs which are not resolution-like, they are still efficient. Unfortunately, this is not the case. The main theorem in this work is that there are formulas that have resolution refutation of polynomial size, and therefore they have polynomial calculus refutation of polynomial size when using the variable for negative literals. But still, if we want to refute the same formula without using the variable for negative literals, the formulas require exponential size refutations. So there is a huge advantage of using these negative literals, a huge theoretical advantage. So what's the idea of the proof? Well, the idea is that if we have a clause, like see, this is an example of the clause, we will substitute, if we have a formula in general, we will substitute the original variable with this junction of two new fresh variable, yi and zi. In this way, we make the formula f slightly harder. Then afterward, after doing this lifting process to make the formula slightly harder, we will analyze its hardness using a restriction strategy. So we will fix either yi or zi to 0, choosing with probability 1/2 each. So basically, for example, in this case, for variable 1, we decided to set to 0 z1. For for the third variable, we decide to set to 0 y3, then y7, and then z9. And see that this restriction turns the lifted formula into an isomorphic version of the original formula, as you can see, because all these clauses are satisfied, and the only clause that survives, that is not satisfied, is an isomorphic copy of the original clause. It's basically the same clause. It's basically the same clause up to renaming. So, from this lift and restrict strategy, the restrict part will allow to analyze the hardness of formulas, and one crucial tool will be the following lemma. If we take a monomial without negative literals, then this restriction will set these monomials to 0 with probability 1 minus, at least with probability 1 minus 1 over 2 to the degree of m. So basically, this restriction will kill most of the monomials without negative literals. And the proof is easy, because if there is a pair yi zi that divides the monomial, then the monomial is certainly set to 0. Otherwise, all the variables are independently set to 0 with probability 1/2. So, how we find this proof, which is hard for polynomial calculus without negative literals, and is easy for polynomial calculus with the negative literals? Well, the starting point is the graph ordering principle. The graph ordering principle formula starts from a graph and say that if we the formula claims is an unsatisfiable formula, and it claims that it's possible to give a partial order to all the vertices in the graph. See, for every pair of vertices, not just for the vertices with an edge, for the vertices that have an edge between them, but for all pairs of vertices, so even 2 and 9, we have a variable xuv, like for example x92 or x29 or x81 and so on and so forth. And among those variables, these variables will encode a partial, the clauses of the formula claims that these variables will encode a partial order. More specifically, we'll say that there is a partial order among the vertices of the graph by saying that the relation expressed by x variables is antisymmetric and transitive. And simultaneously the formula says that there's no vertex which is a local minimum. It's the closest say that every vertex must have a predecessor in the partial order. This is of course it's impossible because the partial order over a finite set of elements have a global minimum, so it will have also local minimums. For example, 1 is not a global minimum, but it's definitely a local minimum. It's definitely a local minimum. And the closest says that there shouldn't be any local minimum, and this formula is of course unsatisfiable. So this graph ordering principle is the starting point. It's easy to some extent because for every graph we already know the graph ordering principle as a polynomial size resolution refutation, and moreover, and this is very important, this refutation of polynomial size can have at most 2 negative literal per clause. So this is the easy. So basically, we will use that this formula is somehow easy and somehow hard. This is the easy part that we need to use. But also this formula is somehow hard in some other sense. For there exists a family of expander graph like the regular expander graph over order of n vertices, and the graph ordering principle on this expander graph has no polynomial calculus refutation of a small degree. Any polynomial calculus refutation for these formulas needs to have large degree. Good. From this, we will define a new formula, Fn, which is essentially the graph ordering principle formula over this expander graph, with applied the substitution, the lifting that we discussed before. So every variable is substituted by the OR of 2 new fresh variables. Well, this new formula is the formula that we'll use to separate polynomial calculus without negative literals from resolution. And in particular, from the easiness of GOP, we will find that Fn is easy in the sense that a small resolution refutation. And from the hardness of GOP, we will prove that Fn has no small polynomial calculus refutation without negative literals. So, first the lower bound. It's quite a simple argument. Let's assume that the formula has polynomial calculus refutation pi with no negative literals of size s. This is again the formula that we are considering. Now, for each pair of vertices, essentially for each variable, we will set to 0 either one or either y or the z variable chosen at random. Now, if we apply this restriction, as we already observed, the formula becomes an isomorphic copy of GOP. But even the refutation becomes a polynomial calculus refutation of GOP. This is a very simple observation on the structure of the polynomial calculus refutations. But simultaneously, every monomial that has no negative literals and has degree larger than log s will not be fixed to 0 only with probability strictly less than 1 over s. Like strictly less than 1 over 2 to the log of s. So 1 over s. It means that the restriction with non-zero probability will fix the whole monomials that have degree larger than log s to 0. So by union bound, we have a restriction that kills all the monomials of large degree, and therefore in the end, after the restriction, we get with probability greater than 0 a polynomial calculus refutation of the original formula GOP, where all the monomials of degree larger than log s have been killed, so the whole refutation have degree less or equal than log s. But therefore, since the degree of the refutation must be at least omega of n, it means that the size of the initial the initial size s of the refutation of Fn was exponential in n. So this means that there's no small refutation with no negative literals of the formula Fn. For the upper bound, well, this is easy as well. We need to find a resolution refutation of Fn. We start from a resolution refutation of GOP G of n, and we know that there is such a refutation that also has at most 2 negative literals per clause. So let's see that this is the list of clauses in the refutation. Now, we apply the lifting to all the clauses of the refutation. So every clause becomes a set of 4 clauses, because if we apply the lifting to a clause with at most 2 negative literals, the explosion, the distribution of the disjunction under the negations will produce at most 4 clauses. So every SI is a set of 4 clauses, such that SI is the set of 4 clauses obtained by CI doing this lifting. Now, if the initial clause CI, if CI in the refutation, the original refutation, was a clause from GOP GN, then the set of clauses SI is a subset of clauses from the lifted formula, because if SI is the lifting of CI, then if CI is in the original formula, then SI is a bunch of clauses from the lifting of the original formula. Another observation is that the last set of clauses in this sequence of bags of clauses contains the empty clause, because CL is the empty clause, the lifting of the empty clause is the empty clause. So in order to make this sequence of sets of clauses a true refutation, well, we need to simulate the inference that from 2 clauses in the original, like the original resolution inference in the original refutation, we need to simulate it in the sense that we need, for example, from the clauses in SI and the clauses in SJ, we need to efficiently derive the clauses in SK. How do we do that? Well, this is a generic resolution rule in resolution from the original formula. Well, the lifting of the clauses produces this. Notice that A can have at most 2 negative literals, so the lifting will produce at most 4 clauses. Here B can contain at most 1 negative literal, because the other negative literal is here, and there can be at most 2 here. So if you apply the lifting, we obtain these 4 clauses where B1 and B2 are repeated. Now, if we do all the possible resolution steps between these variables, we obtain 8 clauses. A1 or B2, A2 or B1, and so on and so on. Now, these are 8 clauses, and are essentially the lifting of are essentially the clauses that represent the lifting of A and B, because A1, A2, A4, A3, A4, and B1, B2 are the lifting of A and B. But there are 8 clauses. What's the issue? Well, the fact is that if B1 is different from B2, it means that there is a negative literal here in B, so there can only be 1 negative literal in A. So A1 is equal to 3 and A2 is equal to 4. Otherwise, B cannot contain any negative literal. So in total, these clauses are at most 4, and there is a repetition then in this list. So to recap, we define the formula Fn by taking a family of constant degree expanders. We build the graph ordering principle formula on those expanders, and we apply the lifting. Now, this formula Fn is a constant with CNFs, such that Fn has a resolution refutation of polynomial size, and in particular then has also a polynomial calculus refutation of polynomial size when using negative literals. But any polynomial calculus refutation of Fn without negative literals requires exponential size. So this is the result, the main result of the talk. Now, as I mentioned before, in the paper we discuss also other proof systems, Nussellens, Shirley-Adams, and sum of square. But the proof is more or less the same. Just the fact that the starting formula cannot be GOP, because for this other formula, for every proof system we need a formula which is the right level of easy and hard for that proof system. For example, in Shirley-Adams and sum of square we don't even know if GOP, if a graph ordering principle is hard or not. So in particular, while we get the separation using a CNF, a bounded width CNF in this two-proof system, for Shirley-Adams and sum of square we use the ordering principle, and the ordering principle is an unbounded width CNF. So we can't really get down to a CNF, but we can with a constant width CNF. But we can derive a separation between Shirley-Adams with and without negative literals with a bounded width CNF. But the formula here is not easy enough for resolution, so we don't get a separation between resolution and Shirley-Adams without negative literals with a bounded width CNFs. So in conclusion, we have seen that the negative literals are very important, at least theoretically, for many algebraic proof systems, otherwise they are not even able to simulate resolution. The problem is that in practice, doubling the variable is very inefficient, or even worse, is useless, because there are algorithms that eliminate these additional variables. So one practical problem would be how to find a way to solve a polynomial equation using like a Grobner basis style algorithm without expanding unnecessary these kind of variables. And the other open question is, for example, if we want to strengthen the separation for Shirley-Adams and sum of square to a constant degree CNF, we would like to find whether graph ordering principle is hard for Shirley-Adams and sum of square. So thank you for listening, and this is a bunch of references for this talk.